We would like to welcome Jimmy Takeda, and he's going to tell us about causal inference with machine learning. So let's welcome our speaker.
Hello, everyone. Thank you for coming to my talk. I'm Jimmy, the data scientist at Mickey House, a Japanese kids clothing brand. Today, I'll be speaking about causal inference with machine learning. So let's get started. This is the agenda for my talk. After a quick introduction, I will explain the background and concept of causal inference with machine learning. And then I will cover two techniques. One is meta-learners, and the second one is uplift modeling. Regarding each technique, I will demonstrate a case study with a sample code with EconML and CausalML. And due to the packed agenda, please save your questions until the end. So just a quick introduction. Let me quickly introduce myself. I have worked at the intersection of data science, marketing, and customer analytics at Procter & Gamble, as well as my current company and as a freelancer. The track of this talk is social sciences and economics, so I will try my best to explain this topic to business professionals as well as researchers in data science and sociology and economics. From this presentation, my hope is that you will gain a basic understanding of causal inference with machine learning, and I hope this talk motivates you to try Uplift causal inferences, meta-learners, or uplift modeling in your environment. So, what's causal inference? Let's explain a common business scenario. Let's assume that you are a data scientist and you are helping a colleague who is in charge of marketing. And she said this: we sent coupons to some users and their purchase rate was twice as high as others. This means the coupon doubled their purchase rate. Do you agree with her? What if she also said this? She says, we sent coupons to customers who purchased within the last 12 months. This is a problem. So what could the problem be? What we want to understand here is the pure effect of the coupons. If we give coupons to some intentional rules, we can't compare the purchase rates apples to apples. This is because customers who received the coupons might have made purchases regardless of the coupons. For example, these customers might be more active and they might be influenced by other marketing factors such as social media or influencers or newsletters. The effect of other factor here is called selection bias. So, causal inference is the process of determining whether a cause and effect relationship exists between treatment and outcome. Traditionally, it has been used in the fields like healthcare. For example, a classic case is determining whether a new medicine is effective or not in treating a disease. Here, using the medicine is referred to as a treatment, and whether a patient recovers or not is called the outcome. In e-commerce or marketing, we deal with treatments like coupons, advertisement, or direct mails, or other activities. In this case, the outcome is a purchase. In economics or sociology, joining a job training is a good example. In this case, obtaining a job or increasing salary is an outcome, and we want to know whether that outcome was due to the program's effect or not. So, the challenge of causal inference is we can only observe one outcome from the same individual, which is known as counterfactual. If time travel existed, we could use a coupon for a customer and then rewind time and then and observe what happens if we don't use coupons for that customer. However, in reality, of course, we cannot do that. So we can only observe one outcome from the same individual. So you might be wondering, why we don't just do an A/B testing? Yes, you're right. So A/B testing is the gold standard for answering causal questions. In the context of causal inference, we call it randomized controlled trials, or RCT. So in this talk, I will refer to it RCT today. Let's briefly explain the steps with an example. First, we randomly divide customers into two groups. The first one is treatment group, and the people in the treatment group will receive a coupon. And the purchase rate in this case is, let's say, 40%. And people in the control group don't receive a coupon, and the purchase rate is, let's say, 20%. In this case, the effect of the coupon is 20%, as 40% minus 20%. The key point of an RCT is to randomly assign customer into two groups. This step ensures that factors other than coupons are unbiased between two groups. Okay, so if we understand RCT, is everything perfect? Unfortunately, no. Despite its simplicity and robustness, we often face situations where RCT can't be used. For example, in business context, conducting an RCT may require several weeks or several months, which is not always preferred. Also, with RCT, half of the customers do not receive the treatment, potentially resulting in opportunity loss. And in social and economic interventions, assigning citizens randomly to control group is infeasible. Especially in healthcare area, it is unethical to randomly assign people with life-threatening conditions into control groups and then give them a placebo. For those reasons, RCT is challenging in some situations. That's why we need to use causal inference in that situation. But here's another problem. When we cannot conduct an RCT, we need to handle observed data. But observed data can be tricky. This example is from the famous book, The Book of Why by Julia Paul. The x-axis shows the exercise, the amount of exercise, and the y-axis shows the cholesterol levels. The graph on the left seems to indicate that people who exercise more have higher cholesterol levels, which doesn't make sense based on our common sense. However, the reason is that we overlooked an important factor, age. The graph on the right breaks down the data points by age groups. When we considering age, we see that people who exercise more tend to have lower cholesterol levels. This situation, where the overall trend differs from the trend within subgroups, is known as Simpson's paradox. So in this paradox, age is a confounding factor that affects both exercise and cholesterol levels. This situation is known as confounding. Age in this case is called a confounding variable. In causal inference, it's important to account for and control this confounding variable. So next, I would like to talk about what causal machine learning is. So in recent years, algorithms combining causal inference and machine learning have been a hot topic. Today, for simplicity, I'll use the term causal machine learning to refer to causal inference with machine learning. From the 1970s to 1990s, researchers like Julia Paul or Donald Rubin established the foundation of causal inference. Around 2010, the fusion of causal inference and machine learning began, and in 2019, user-friendly libraries such as EconML or CausalML were released. Compared to traditional causal inference, causal machine learning can manage more complex, high-dimensional data at the individual level. So, you might be wondering, why should we use causal machine learning instead of normal supervised machine learning? That's a good question because the objective is completely different. Traditional machine learning focuses on prediction based on correlation. For example, the MM model can answer what will the customer buy next and is what the probability of that. On the other hand, causal machine learning aims to understand causality. For example, causal machine learning aims to try to answer the question, did the coupon increase sales, or how much was that impact? So also, the variables used are different. In machine learning, coupon availability is just one of the features. However, in causal machine learning, coupon availability is a very important factor, important variable called treatment variable. And the reason why it's important is that the goal is to identify how this treatment variable affects the outcome. Today, we are going to look at two techniques. The first one is meta-learners, which measures the treatment. And the second one is uplift modeling, which tries to select the right users for targeting. So in the next section, I will explain each of these in detail. So let's first take a look at meta-learners. The goal of meta-learner is to measure the treatment effect. So how can we define the treatment effect? Let me introduce the potential outcome frameworks developed by Donald Rubin, also known as Rubin Causal Model, RCM. Conceptually, it's very simple. For example, if the potential purchase rate with the coupon is 20% and the potential outcome without the coupon is 10%, the treatment effect is 10% calculated as 20 minus 10. It's very simple, right? Next, let's explore the three types of treatment effects we will use today. First, average treatment effect, ATE, is the most common metric, which measures the treatment effect across all customers or all population. Second, the conditional average treatment effect, CATE, is the effect within the specific segment, such as CATE for male or CATE for female or CATE for people in their 30s. Also, individual treatment effect, or ITE, is a treatment effect at the individual level. Now, let's move on to how to calculate these treatment effects. Let's consider this question. Did a coupon increase sale? And this data includes different customers with their attributes such as age, gender, and location. And this data also has information on Z, treatment, and Y, outcome. The column Y1 represents the outcome with the treatment, this one. And the column Y0 represents the outcome without the treatment. And if we know these two columns, we can easily calculate the individual treatment effect by subtracting these two columns, these two numbers. But the challenge is we can only observe one outcome from the same individual. So to address this dilemma, we can use meta-learners. Here, meta-learners are a framework designed to estimate treatment effects using machine learning. So the red numbers were originally missing, but we can predict these numbers using ML, and then we can get the individual treatment effect. This is a very simplified example, but now let's explore the different types of meta-learners. There are mainly 5 types of meta-learner methods: S-learner, T-learner, X-learner, DO-learner, and DML, double machine learning. So the S-learner is the simplest approach, and the DML is the most complex but robust approach. Let's start with the S-learner. S-learner, as S-learner stands for single learner, it uses only a single machine learning model. Look at this table. the S learner uses all the available data to train a single model and then predict outcomes with treatment and outcome without the treatment. The MM model that is used within this meta learner is called base learner. So this one. We can use any supervised ML model, such as LightGBM, XGBoost, or Random Forest for this base learner. Now let's move on to the T learner. T in T learner stands for 2, so we use 2 machine learning models inside. One model predicts the outcome of customers who receive the coupon, and the other model predicts the outcome of customers who do not receive the coupon. This allows the model to better capture the differences in responses between the treatment group and control group. Here, let's return to this table discussing the other types of meta-learners. X-learner is an advanced version of T-learner, and it's better for imbalanced dataset because it uses a propensity score. And both DL learner and DML, double machine learning, use 2 base learners. The first one is a treatment model, which aims to predict the treatment from confounders, and the second one is an outcome model, which aims to predict the outcome from the treatment and confounders. So the important point here is which method should we use for meta-learner. But the point is, the best method really depends on data. So here's my recommendation. The first step, I recommend starting with a simpler approach such as S-learner or T-learner. And then as a next step, try various methods and compare them using accuracy metrics such as MAPE or RSME, and refutation for the robustness. I will introduce the refutation later. So in the next section, I will briefly introduce how to run meta-learners. Here, let me introduce 2 great OSS libraries. The first one is EconML, developed mainly by Microsoft, and the second one is CausalML, developed mainly by Uber. The most significant difference is that EconML covers a wider range of algorithms, while CausalML focuses more on marketing use cases and uplift modeling. Today, I will share 2 case studies, and first I will use EconML with the economics dataset. So I will focus on the core parts of the code, but you can check the full code with this QR code or this link. Or you can also find this link on my page in the SciPy schedule. So let's start with the case study in economics using EconML. It uses the Lalonde dataset. This dataset comes from the employment program to support disadvantaged US workers. The raw data looks like this. The data includes a user with treatment or control label and 6 features such as age, ethnicity, married, and degrees, and also real earnings before and after the program, job training program. Next, let's define the causal model using EconML. The goal of this case study is to understand the impact of the training on the salary in the following year. Therefore, we specify participation in the training as the treatment, and real earning in the following year as Y, and other columns as confounders, X here. Next, let's estimate the ATE, average treatment effect, using this effect estimate underscore effect function. Here, we are using double machine learning with this line. And also, regarding the base learners, we use LightGBM for the outcome model and the logistic regression for the treatment model. But we can change it by changing these lines. Now, this shows the average treatment effect. This is the result. And let's check how robust this model is using refutation. Here we use two methods. First, random common cause method as a random variable to the dataset as a confounder. If this model is robust, the refuted result should not change significantly. In this case, the refuted result does not significantly change from the original value, and also the p-value is greater than 0.05. So we can conclude that this model is robust. And secondly, the placebo treatment method replaces the treatment variable with a random variable. If this model is robust, the refuted result should be closer to 0. In this case, the refuted value is 13, which is much closer to 0 from compared to the original value of 1684. So indicating that this model is robust. So let's move on to the next modeling, uplift modeling. So what's uplift modeling? The key question is, who should we target to maximize sales? Uplift modeling helps customers who are more likely to purchase when treated than when not treated. This is especially useful for cost-intensive marketing. And there are two methods for uplift modeling. The first method is the meta-learners, and the second one is a decision tree-based approach. Because decision tree-based approach is commonly used because it supports multiple treatment groups. This means that instead of just testing only one coupon, we can compare 5% coupon, 10% coupon, and 15% coupon. This is very practical. So let me introduce a key concept of uplift modeling, uplift tree. Uplift tree is based on the traditional decision tree. So this is a traditional decision tree, and this decision tree tries to answer, will the customer make a purchase or not? And depending on how we select decision nodes, the tree can be constructed in many different ways. Here, there are two different decision trees. On the left, the split is based on age, and on the right, the split is based on location. Here, the right tree provides a better split because purchasers and no purchasers are cleanly separated. Then, how can we quantify this judgment? For split criteria, we can use Gini impurity. So Gini impurity can be calculated like this formula. And the left tree has a Gini impurity of 0.44, a high impurity, and the right tree has a Gini impurity of 0, which means a low impurity. So using this metric, we can decide which tree is a better one, more objectively. And then, based on this concept, we can, the uplift tree is an advanced version of this one. So in this case, we consider the treated group and the non-treated group separately. So here, you can see like two uplift trees, and the left one is based on age, and the right one is based on location. And again, the right tree provides a better split. Then, how can we quantify this judgment? We can use the divergence in information theory. So in this case, squared Euclidean distance can be used, and in the left one, distance is 1, and the right side, distance is 4. So we can choose the right one. So, due to the sake of time, I will skip this slide. And let me quickly go through the demo using the advertisement dataset. So I use the Criteo dataset, which is the advertisement company. And Uplift Causal ML, the interface of Causal ML is very similar to the other ML models, such as scikit-learn. We can train using the fit function, and we can predict using the predict function. And this shows the feature importance, and we can evaluate this uplift modeling using uplift curve. So in this case, we can, if we targeting just 20% of the total users can achieve 80% of the result as if we targeted everyone. And the evaluation method is AUUC, area under the uplift curve. And you can extract the customer ID to be targeted with this, like this. So, in summary, I explained the concept of causal inference with machine learning, including meta learners and uplift modeling. And if you are new to uplift causal inference with machine learning, EconML or CausalML can be a good first step. So this is a reference for this talk. And if you have any questions, please feel free to contact me. Thank you so much.
Okay, we have time for some questions. If we have questions in the audience, please raise your hand and I'll bring you the microphone.
Well,
yes.
Yeah, thanks for the talk. I guess you didn't have much time to talk about it, but you mentioned as a way to validate whether your model works or not, you use something called refutation.
Mm-hmm.
So generally, for all of those causal models, I'm always a bit curious, how do you know that what you have is actually correct, right? So here you have some kind of internal validity, right, to show that, okay, it sounds like the estimated effect and the new effect based on this refutation. It looks like it gives some reasonable values. But generally, how do you, especially if you work with marketers, etc., how do you go further in evaluating that what you have is actually reasonable in terms of values? Can you talk a bit about that?
Yeah, regarding the meta learners, we can evaluate it from in two ways. The first one is accuracy metrics, such as RSMSE or something, the normal machine learning method. And this refutation tries to refute the model. And this result shows whether this causal model is valid or not. And I introduced two methods, random common cause and placebo. And this estimated effect is original value. And then we can, with this method, we can add random variables to the confounders. And then this is a new effect. So these two values are similar. So we can say that this model is robust or not. So did I answer this question?
Yeah, I guess I was curious to know a bit more deeply, how that works. How do you know, if there are cases where this doesn't work, for example, where maybe new effect and estimated effect are close, but actually we know maybe because we did some RCT separately that actually doesn't really work. I was curious about that.
Yeah. Actually, there are more than 5 meta learner methods. So you can validate them, check each method by using CV or cross validations, and then decide which meta learner is good and also which base learner can be used for the better result. So.
Okay, thank you.
Hey, so you're using, in this approach, a machine learning model to impute the counterfactual data. Do you have a intuition about what kind of machine learning model might work well for that? And I guess I'm worried that some variables in that table might like you might not want to include those in the model because they have like an effect on that you wouldn't want to include, I suppose.
Yeah, in my experience, I use like LightGBM, XGBoost, or random forest. And I also try as much as method as possible, and then like decide based on the like accuracy and also reputation, and also sensitivity analysis.
Okay, I think that's all the time we have for questions, so let's thank our speaker again.
Thank you so much.